All right, Calc 3, welcome on in. It's Thursday, November 4th, and we are at the end of week 12. You're going to start week 13, of course, next week. But today we're talking about 14.2 still, talking about double integrals, right? We introduced that concept last time, but now this time we're going to get into the nitty-gritty and how do we calculate a double integral. So first things first, let's remind ourselves what we are dealing with, right? At least the notation. Then we'll talk about how we break that down and calculate it. So we are talking about a double integral, and we're given a region R and a surface f of xy. And this is with respect to the differential of area, dA, yeah? And last time we talked a little bit about how we can use this. This is the limit of a sum of surface values f of xy times delta A. Luckily, we don't have to use that. We're going to find a way to sort of get around that, just like we did in Calc 1, where you didn't have to use the Riemann sum every time you wanted to do a single integral, right? There's a way around that here as well. And so that's what we're going to focus on today, right? Now remember, R is the region of integration, right? The domain or the region of integration. And we're double integrating over that surface there, right? So let's get to... let's start off with the properties. How does this thing work, right? Well, you'll notice that it shares properties that the single variable integral has, right? Like, for instance, it's going to be really helpful on this list of things here to think of this as a volume, right? Volume under a surface, right? And so what this is saying here, this first property, is that constants can be pulled out in front of both integrals, right? Like that. And why is that? Well, if you take the height, the surface being the heights, and you multiply them by a scale of c, right? What does that do to the volume of the box, right? Or the volume of underneath that surface? Well, it scales by that much, right? So like if I change the height, and I multiply the height by 7, right? Well, then that's going to have a corresponding multiplier of 7 to the volume. And so that's the one way you can think about that. That's what justifies taking the c out. Constants come out of integrals, just like Calc 1, yeah? What's the double integral of a function, a surface, plus or minus another surface? Well, just like integration Calc 1, double integration splits over addition and subtraction for the very same reason, right? I mean, if you want to find the area under the curve, the addition of curves or subtraction of curves, it's the same thing as had you found the area, and in this case, the volume added subtract to the volume of the bottom surface, right? So integrals split up over addition and subtraction, just like Calc 1 did. Now, if this volume, this double integral is greater than or equal to 0, that's going to happen if the surface is greater than or equal to 0, right? And that's because of the Riemann sum idea, that the function values that you're plugging in are always positive or equal to 0, then that means you're going to have an actual volume underneath that surface. And so the double integral is going to be greater than or equal to 0, right? Yeah, so that is, that's one way to think about that as well. Now, here we go. If one surface is always greater than or equal to another surface. So we have some surface up here, we have a top surface, and we have some bottom surface, right? Like this. Then if we take the double integrals of both sides, we're going to get the double integral of f is going to be greater than the double integral of g. And you could probably see that, like what would be the volume underneath the top surface versus what is the volume underneath the bottom surface, right? And so this is going to be a larger number than the double integral of the smaller, right? And so that is a property as well. Then, finally, we can split up a double integral as long as we can take non-overlapping subregions R1 and R2. This is the idea of taking a single integral, and if I have to integrate from like 1 to 10, right, I could split it up if I wanted to, the integral from 1 to 4, and then the integral from 4 to 10. I could do that. I could split that up and just add the results. This is the same exact idea. I think there's a picture of non-overlapping regions. Yeah, so instead of integrating over this whole region, I could, if I needed to, split this into an R1 and an R2, take the double integral over this region itself, and then add it to the double integral over this region itself as well. So those are the properties of the double integral. These are going to be helpful when we're actually calculating, that you can take constants out and split them up and all that sort of stuff, yeah? But now let's get to, how do I calculate this double integral, right? One of the key ideas that we have to recall from, I think, Calc 2, is that we can find the volume as long as we understand the cross-sectional area, right? And so one thing you might remember from Calc 2, and if you don't, you'll be reminded of it right now, that the volume of an object is equal to the integral from some a to b of the cross-sectional area, right? So this is like the idea that I can find the volume of a three-dimensional object as long as I understand how the area of each layer works, right? So if I can think of it like, it's almost like a 3D printing, right? If I have like one layer, I understand the area, then I go up very slightly above and know the area there, know the area there, know the area there, and know all of the areas, like putting together just a stack of shapes. And that builds the 3D shape that you're looking for, right? And one of the things that you did there was find volume via cross-sectional area. We're going to actually really take advantage of this, because we can find then, to find the cross-sectional area, well, that in and of itself is an integral, right? Finding area under a curve, right, is also an integral. So if I start off with the volume of an object being this integral from a to b with respect to x, and I have to come up with this formula, the a of x part, will most likely be an integral in and of itself. So let's see if we can explore that, right? First off, though, let's see if we can put an example to this and work with this idea a little bit. So let's start off with the surface z equals f of xy, which equals 2 minus x minus 2y. Okay, now that's going to be a plane in the 3D world, right? And let's see if we can just go ahead and like graph that real quick. Now I have something on GeoGebra prepared for us as well, but it's good to sort of write this out by hand a little bit, because remember, planes are really easy to calculate, right? So if x and y are 0, z is 2. So let's put a dot there. When, let's see here. When y and z are 0, that'll mean that x has to be 2, doesn't it? Yeah? So there we go. Right? In other words, the point 2, 0, 0 is on this surface, isn't it? 2, 0, 0. Yeah? And so that point is on there. Now let's go ahead and plug in a point on the y-axis. That would mean that z is 0 and x is 0. Z is 0, x is 0. And that would tell me that y would have to be 1 to do that, to make that true. And so I go 1 unit out, put that dot there. And now I have this, at least the triangular part here, this part of the plane, like this, like that, and like this. Even with a ruler, I messed it up. Gosh, unbelievable. All right, so there we go. We have our three-dimensional object right there. And what if I wanted to find the volume of this thing? Right? Well, the Calc 2 approach would be the following. If I could find the formula for the cross-sectional area. So now what do I mean by that? Let's cut this like here. Right? Like this. Right? And I have, what I have there is a triangle, right? Like that. But if this triangle moves up and down this thing, this is going to be the large triangle right here, right? And then here it's going to be a dot. The triangle just shrinks into nothing at this point, right? But as it moves, it does change formula, doesn't it, right? Or actually, I shouldn't say that. The formula is the same, but the x value that we're using changes, right? So let's see if we can get a hold of that. I want to calculate the area as a function of x of this triangle, this cross-sectional triangle. Okay. So now to do that, let's start off. The area of a triangle is half the base times the height. Okay. Now these will change depending on where it's at, depending on what the x value is, right? So this is going to be half. Now let's think about what this base is, right? So this, if I draw a little sort of side view here, I'm interested in what this length is here, right? But this length starts at y equals 0, right? And goes up into this line there, right? That line. So now let's see, can I like draw what that line is? Yeah. So another picture here. Let's see if we can get this done. So here's the x-axis, here's the y-axis. And what I have here is y equaling 1, so there, x equaling 2. Okay, so we have that right there, right? And so the height that I want, or the base that I want right here, is actually this right here, right? On this sort of top view, if you will, right? And so how long is this? Well, when the x is 0, would you agree that that this is a length of 1 unit, right? When x is 2, the length is 0. There is no height. And when this is 1, it's whatever length that is, right? Probably half, if you will, yeah? How do we get that, right? How do we get that? Well, let's get a description of this, right? So this line, right, what would be the equation of that line? Well, okay, let's see. What is its slope? What is its y-intercept? So we get y equals, the slope would be rise over run. So it looks like for every 2 we run, we rise -1, right? And so let's say that that's -½ x plus a y-intercept of 1, right? And so this would end up being, this would end up being the height that we want, right? Think it through. If I have x to be 0, that goes in, and look at that. The y equaling 1, that is the length of this, for this large triangle there, right? That is 1 long. If x is 2, right here, notice that the 2 would go here, and I would get -1 plus 1, so y would be 0. And the height, sorry, I keep saying height, the base, right? The base of this would be 0. That would correspond to being right there. And it takes care of everything along the way as well. So the base becomes this formula. The base length is -1/2 x plus 1. Okay. Now let's do a similar thing for the height. Now the height is going to be this. And notice that it's going to be 2 units tall if it was here. And it's going to be 0 units tall here, and probably 1 unit tall, it looks like, just for that. Now, how do I actually get at that? Well, let's maybe draw another picture in the xz plane. Okay. And here in the xz plane, we have a line that starts here at z equals 2, like that, and goes to x equals 2, like that. Okay. So that's what this looks like in the xz plane. And now this thing right here represents the height of this triangle, this right here. Yeah. So what would that be depending on where the x value is? Well, that would be the equation of this line, which says that z should equal the slope of this line, which is -1 x, plus the z-intercept, which is 2. So we get 2 minus x. So the height is 2 minus x. Again, feel free to check that, right? Because if you can check that, you get, if x is 0, right, I get that the height is 2, which is correct. If x is 1, I get that the height is 1. And if x is 2, I get that the height is 0. Yeah, nice. So this works out pretty nicely. Now, let's do some simplifying arithmetic here, or algebra. I'm going to get a common denominator here. So this is going to be all over 2. So this will be, I need a 2 here, so it's going to be 2 minus x over 2 times 2 minus x. And so simplifying that gets me that the area function that I'm looking for is 2 minus x squared over 4. Okay? Now that was a little bit of annoying work to have to do to get that. But nonetheless, I did find the area formula. I did find the area formula for that, for a given value of x. Now, that means I can now go on and take the volume, find the volume. So therefore, the volume of this thing is going to be the integral from x value to what x value? From 0 to 2 of the area function. Now, this is not used double integrals yet, but we're getting there. We're getting there. Let's work our way up. All right, so I want to at least finish this off, right, to do this. Let's see if we can calculate this. A 1/4 comes out. That's a constant. And I'm integrating, we could do a u sub, right? Let u equal 2 minus x. Then du is negative dx, so a negative comes out. And I'm integrating u squared, which would be u cubed over 3. So that's going to be 2 minus x cubed over 3, evaluated from 0 to 2. Okay, so that negative comes out, negative 1/4. Times the 3. Let me do that. Negative 1/12. Then I'm just plugging in 2 minus x cubed from 0 to 2. Okay. And to finish that off, the 2 goes in, I get 0 minus a minus 1/12, plug in 0. 2 cubed, I get 8/12 as the volume. You get 8/12 as the volume, which indeed is 2/3. Okay, so that's one way of getting the volume, right? That's that was a little challenging, but the point is, if I can come up with a cross-sectional area formula and then integrate that formula from the x values, in this case, from 0 to 2, then that builds up that solid layer by layer, and the result of that integration ends up being the volume of that object. Okay? Now, this works no matter how you come up with this area function. This was sort of geometry, right? And then sort of drawing pictures and figuring out that geometry. We can obtain a of x in a maybe easier way, maybe in a little bit of an easier way, if you're willing to do a little bit of integration, right? So maybe think of it this way. I'm going to go back to this problem here, where we had this triangle, like that, and here's y equals 0, and this was the point y equals 2 minus x over 2, and this happened to be the portion of our, this is the surface, the plane, right? And so this is going to be z equals 2 minus x minus 2y. So here's what I want to do. To find the area of this thing, this is going to be a single integral as long as I integrate from this to this, right? And over this function. You see that? But notice that this is just integration, but I'm keeping the x constant. I'm treating x constant for the moment. And at some given x, I'm integrating from 0 to 2 minus x over 2. That'll take care of a small triangle like that, a very small triangle like this, or the very tall triangle like that. Then I want to integrate over all possible y values to do that. So what my point is I can find area of x this way. This is the same thing as the integral from 0 to 2 minus x over 2 of the surface 2 minus x minus 2y with respect to y, treating x like constant. Now, to show you that that is true, let's go ahead and do that. This is going to be, the integral of this is going to be 2y minus xy minus y squared, right? Raise the power by 1, divide by new power. So I get y squared. And I want to evaluate that from 0 to 2 minus x over 2. Okay. So let's see what we got here. Oh, look at this. I can factor out this. Let's simplify this before I do this. I can think of 2y minus xy as 2 minus x times y. Right? I can do that. And so now I'm going to have what? I'm going to have 2 minus x, plug in this for y, which is 2 minus x over 2, minus this squared, 2 minus x squared over 2 squared, which is 4. So I'm going to actually have 2 minus x squared over 2 minus 2 minus x squared over 4. This is half of the thing minus a fourth of the thing, gives me a fourth of the thing. And so then my result is 2 minus x squared over 4. And do you see how those match? I got there via an integral way. See that? So it appears that if I wanted to find a volume under this surface, underneath this, this plane, I can perform 2 iterated integrals. I can first integrate this with respect to y, and then integrate that result in terms of x. In other words, let me see if I can write out what we would have, right? In other words, to find the volume here, it looks like I could have done the following. I could have integrated from 0 to 2 the result of the integral from 0 to 2 minus x over 2 of the surface, 2 minus x minus 2y in terms of y, and then the outside in terms of x. This equaled 2/3 upon doing that. This is our first suggestion that to calculate the double integral, the volume under the surface, it can be thought of as an iterated integral of a certain setup, right? Notice that the surface goes here, right? There's a little bit of shenanigans here about how to come up with the limits, and we'll go through that obviously for the rest of the video tonight, yeah? But what this is saying is that the double integral over this region R of the surface 2 minus x minus 2y dA can be thought of as this iterated integral. And the result of that is 2/3. Okay? So with that in mind, right, we want to now sort of tighten up that idea. One of the greatest names in mathematics is coming up, and there's a theorem that says that double integrals can be unpacked and thought of as either a dy dx integral or a dx dy integral, right? And the name of that theorem is Fubini's theorem. Fubini's theorem allows us to say that. We're going to write that down a little bit. But before we do that, I have one little visualization in GeoGebra that I want to show as well. Oops, how about that? I lost my visualization. Hold on. Where'd you go? There it is. Okay, so here I've graphed this in GeoGebra, okay? And so this is what I want to find the volume of, this triangular wedge thing here, right? I want to find the volume of that, okay? And what we just did was a dy dx integral. This is the visualization of it. Notice that yellow triangle there? As I push x to the right, see how that cross-section is still a triangle, but it gets smaller and smaller and smaller. Do you see that? So to find the volume of this thing, the first step is to find the area of this yellow triangle. That's what we did first, right? We found the area of that yellow triangle. Given an x value, what is the area of that triangle? We found the formula for that. Then, once we have that formula, then we want to push this through all possible x values. And the result of that calculation will get us the result of this double integral. In other words, the double integral over the function surface, dA, is the integral from something to something of the integral from something to something of that surface dy dx. Or it's the single integral over the area function, right? We can think of it both ways like that, okay? But notice that that's not the only way to sort of build this surface or build this object, right? I could think of it as a 3D printer, just making layer upon layer and then creating that three-dimensional solid, right? But I could also think of it this way and sweep this way. See that? And that fills in the same object. It's the same object, right? But now I'm sort of going through this way. This is a dx dy integration. And notice that both of these thoughts, both of these ways that these are coming up with here, they should agree on what the volume is. Because at the end of the day, they're generating the same exact solid, aren't they? It's just one is building up this way, and the other one is building up this way. See that? Yeah. So these double integrals should agree in value, but there's two different ways to set them up. This is where Fubini's theorem comes in. Fubini's theorem says there is a way to calculate this double integral using dy dx, and there is a way to do this using dx dy. So now the rest of this is just practicing that idea. Yeah. So let's get to Fubini's theorem. All right. So if I have a continuous function on a plane region R, and let's say that R is defined on some region where x gets to go from a to b, and y is from some function to some function. Okay, so there's a bottom function and a top function. Then it says the double integral that we seek to find the value of can be thought of as an iterated integral, the integral from a to b of the integral from bottom curve to top curve of f of xy dy dx. On the other hand, if R is defined by y values that go from some constant to a constant, and x is from h1 to h2. Now, notice for this first one, I said from bottom curve to top curve. The orientation on this would be from left curve to right curve, right? This would be x on the left, all the way going to the function x equals whatever on the right. So instead of bottom to up, we go from left to right. Sound familiar? Isn't that what we were doing the other day with iterated integrals with the orientation that we could choose the arrows? We could either go from bottom up or from left to right. Yeah. So what that says is the same double integral can then be written as this way, right? As a dx dy integration. Okay. I think now it's time to set up some examples and get going on working through that concept. All right. Now our first problem is very simple because it's a rectangular region. So here's what we are going to do. Let's say I want to evaluate the following double integral. And they give me the double integral over R of the surface 1 minus 1/2 x squared minus 1/2 y squared dA. Okay. Now, this is incomplete because they've not told me R. So you have to look around for information about R, a region in the xy plane. And the very next thing says where R is, okay, where R is the region given by 0 less than or equal to x less than or equal to 1, and 0 less than or equal to y less than or equal to 1. Okay, so the region in the xy plane, the domain of integration, the region that we're working with, very easy. It's a square. And so I'm going to draw that. This is the x-axis, this is the y-axis, and I'm working on this square right here. Okay. This is the domain of integration. Or you can think of it as a top view of this problem. I'm only concerned with the surface that's above or below this square. Okay? I'm not interested in anything out here at all. It's just that's what I'm interested in, right? And I don't want to say volume because I don't know if this is always positive, right? It might be, and the answer I get might end up representing a volume. But you could have a surface, that starts above your region, but then somewhere in the region it starts to dip below. And we had this idea in Calc 1 as well, didn't we? We had, what's the area under the curve? Well, if the curve was above, that counted as like positive area. And then if that curve went down below, that started taking away, right? So the integral, to say it more accurately, is really a net area, if you will. Think about it that way, right? So this counts as positive area above, and it takes away area and even going negative if it's below the x-axis. Same thing here. I can have like a net volume idea. So the surface is above, that's counting as positive volume. And then if the surface dips below, that's starting to add in negative volume, if you will. Okay. All right. So let's go ahead and set this up. What Fubini's theorem says is that to calculate this integral, I can set up an iterated integral involving this surface. So here's our first choice that we have to make. Do you wish to make a dy dx integral or a dx dy? Do you want the dy first or the dy second, right? You get to choose. Sometimes the problems, it really matters sometimes. Other times, like this one, both ways are equally trivial and easy, and so it doesn't really matter. What's nice is whatever way you pick, it'll work out, right? As long as you're setting up the limits correctly. So let's go ahead and go with dy dx. Now remember from previous work, dy dx means from bottom curve to top curve. Yeah, like that, right? And then I push these arrows horizontally from x equals 0 to x equals 1. Do you see that? So what I'm going to get here is, what does y do? It goes from the bottom curve, y equals 0, to the top curve, which is y equals 1. Yeah? And then we push that arrow from x equals 0 to x equals 1. And so that is the iterated integral we would need to solve to evaluate to come up with my original integral. This would be the value of that double integral. Now, to save us some time on the video here, let's suppose I do that iterated integral. Remember, you do the one inside first, right? And then you plug in and do the outside one next. When all is said and done, you get 2/3. Okay. Yep. So in that, this would, in fact, the book says it would represent the volume of the solid, because this ends up being a positive, always positive surface. It's always above this. Yeah. Okay, awesome. Now, I think it's time to do some other examples here. Although I don't like the book's examples. They start to get like real tough right away. Let me work my way there. Okay. And in fact, let me do a problem where they show us the picture that we want to work with. All right, so I want to now calculate the volume of the following. So sorry, scroll. Okay, yeah, let's do one of these. Let's see here. Zoom in. Let's zoom in on 24 here. Okay. All right. Take a moment to pause this video and to draw 24 on paper. Okay. Yeah. So go ahead and take that time. I'm going to draw it here as well, or at least I'm going to draw the important parts. Okay. And you'll see what I mean in a second here. Okay. All right, again, if you didn't have enough time to draw that completely, go ahead and just pause the video, and then you can catch up right there. So I've drawn what I need to do to find this volume. I know to find the volume, I need to double integrate over the region R of the surface 4 minus x minus y. Okay? That's the problem in front of me. But what is the region R? The region R is what this thing looks like as a projection into the xy plane. So if you could imagine taking this picture, right, taking this graph and looking from above, what would that look like if the z-axis was pointing right at your eyes, right? What would that look like, right? And so I would say that that looks like this. This is what it looks like in the xy plane, right? Right? That is the region R, okay? Now notice, to do this double integral, I don't actually need a picture of the 3D object. I don't really need that, right? All I'm going to do is double integrate over the surface, and I need to understand how R works, right? So this is R. So now I get to choose my setup. So let's see if I can set this up as a dy dx integral. dy dx. Okay. And now that means I'm going to be using bottom to top arrows, right? So let's think about how arrows work in this situation. It looks like the arrows always start on this bottom curve. Well, that bottom curve is y equals x. So it looks like the y always starts at x, and it goes up 2 until it hits always y equals 2, that horizontal line y equals 2. So we can say that that inside integral with respect to y is integrating from y equals x to y equals 2. Then I have to think about horizontally, where do these arrows go? They start at x equals 0 and get pushed to x equals 2. You see that? And so this is going to integrate from 0 to 2. So that last integration is always what physical x values here, in this case, does the arrow go through, right? There shouldn't be any variables in here. These should be from a solid number to a solid number, right? From a constant to a constant, okay? But there we have it. That's the setup. This is that we knew that the volume would be the double integral over R of this. That's conceptually the way to say it. And then we had an option on how to unpack the dA so we could actually calculate it. And Fubini's theorem says that dA can be written as dy dx, can also be written as dx dy. Let me do this. We could say or. So obviously when you're doing this problem for practical purposes, you don't need to do both ways. But for our practice here, I just want to show you that these will end up giving me the same thing. Not the same looking iterated integrals, but the same quantity once I solve them, once I evaluate them. So let me set this up, same problem, but now I'm setting this up as a dx dy instead. Okay? Dx dy is from left to right arrows. So now I'm visualizing horizontal arrows like that. And thinking about going from x equals what to x equals what. So this always starts at the bottom, the left part of the arrow always starts on this vertical line, which is x equals 0. Right? And it goes out until it hits this diagonal line, right? That diagonal line is x equals y. Then we push y from, how tall do these arrows go, right? So we start at a y value of 0, and these get pushed until a y value of 2. So 0 to 2. Now my claim is this and this are both the same value, even though they look quite different, right? There's a bit of difference to them, yeah? But they should yield the same value. So you'll probably set this up, and then you'll have to think about, well, maybe this one's really ugly and terrible to do, right? And so maybe the other direction is easier. And in fact, if I had to give my preference to either one of these just from the beginning, it would actually be dx dy, just for the simple reason that there's 2 zeros here. And I love plugging in zeros because that usually wipes stuff out, right? So if I had the choice to choose which one to calculate, I think I'd lean more towards this one, although both of these are quite easy, right? But I would go with that one just because of the double zeros there. So in fact, let's do it. So here we go. I'm going to integrate from 0 to 2. Integrate this with respect to x. So I'm going to get 4x minus x squared over 2 minus y times x, evaluated from 0 to y, dy. Now I get to plug in, I plug in for x, right? So everywhere I see x, I'm going to plug in that y. So I'm going to get 4y minus y squared over 2 minus y squared. And then here we go, minus 0 plus 0 plus 0. See, that wasn't bad. I like that. Okay. And then we can simplify this before jumping into the next integral phase. So here we go. We got negative 1/2 y squared, negative 1/2 y squared. That's going to be negative 3/2. So I can think of this as 4y minus 3/2 y squared. Yeah. And now we can integrate. So this is going to be y squared over 2. The 2 is going to cancel with the 4 and leave a 2 upstairs. Minus y cubed divided by 3. The 3's will cancel, giving me that. And I get to evaluate from 0 to 2. Okay. So now I have 2 squared, which is 4. 4 times 2 is 8. Minus, plug in a 2 here, we get 8 halves, right? So that's going to be 4. So minus 4. And then minus plug in 0 plus plug in 0. I get that this volume is 4. Volume of that is 4. Okay? Nice. Now, to check this, go ahead and do that. Right? Calculate that integral. It'll look a little bit different along the way, but at the end, it should get you 4 thanks to Fubini's theorem. Right? Okay, excellent. Let's try another one. Another one where they've given you the picture, so let's try that. Okay, let's look at 26 here. Now 26, do you see how it's curved versus 24, which was like this, this flat plane top? Yeah. Here we have this curve, right? The good news is, doesn't matter, because as long as you have the description of that surface, we're doing okay, right? Because we know that the volume of this thing is going to be the double integral over R, the region in the xy plane, see that, of 4 minus y squared. So I don't have to think too much about the three-dimensional geometry. To do a double integral, I just really need to get a real good hold of R, the region of integration. Okay, so go ahead and pause that if you need to draw anything here. But I'm going to move on. So let's see here. We got R. R in this case, so this is 26. R in this case looks like, well, looks like a triangle. Is this the same exact? I think this is the same exact region. Right, because this is y equals 2. Yeah, so this is y equals 2, so we get that horizontal line. We get y equals x, so that's that diagonal line. And yeah, and it's this part over here. That looks really familiar. So now we just need to double integrate over the region R of the surface 4 minus y squared dA. That will get us the volume that we care for. The volume of the three-dimensional object, not pictured here. Okay, let's set this up. So again, you do have choice here, whether you should do dx first or dy first, right? I don't know. From the start of this, I'm kind of liking dx first because there is no x value here. And so that would be just integrating a constant, which would be pretty easy, right? So I'm thinking my intuition says let's try this as a dx dy. So when I do this as a dx dy, I'm thinking from left to right, like that. So this is starting at x equals 0, sounds familiar, going to x equals y. And then y gets pushed from the bottom of 0 to the top of 2, 0, 2. Okay. Yeah, this isn't going to be bad at all. So going ahead and doing that, this whole thing's a constant. So I can think of it as 4 minus y squared times x, evaluated from 0 to y. Plug in the y for the x. So we get the integral from 0 to 2 of 4 minus y squared times y minus 0. Nice. So that wipes out. And yeah, it leaves me with a great integral here. Integral from 0 to 2 of 4y minus y cubed. So that's going to be y squared divided by 2. So 2 minus y to the 4 over 4. Evaluated from 0 to 2. So now I just have to plug in 2 times 2 squared, which is 4. 4 times 2 is 8. Say 8 minus 2 to the 4 divided by 2 squared is 2 squared. That's going to be 4. Oh my gosh. Did we really get 4 again? That's funny. Not sure how that can be. I'm a little surprised by that. All right. Maybe you want to double check my arithmetic, but it looks like everything was fine. Let me try this again. 2 squared is 4. 4 times 2 is 8. This would be 2 to the 4, right? 2 squared. 2 to the 4 is 16. 16 divided by 4 is 4. 8 minus 4 is 4. Okay. We'll go with it. Yeah, nice. All right. So that's your basic type of double integral problem right there, right? Now, the rest of these, they have you sort of come up with the picture yourself, right? Or working with and drawing the thing yourself, yeah? So let's see here. Let me do 15. 15 looks interesting. Maybe I should do 16 because I don't want to do an odd, maybe. Yeah, maybe let's just do an even one. Okay, so let's take a look at 16. 16 is one where they did not give you a picture. And so let's see what we got there. They're asking us to calculate the double integral over r of x e to the y dA. Okay? They tell us that r is the triangle, more triangles, okay, bounded by x, y equals 4 minus x, y equals 0, x equals 0. Okay. So yeah, no picture here at all, right? So this is some surface, okay? I don't really need to visualize it for this, thank goodness. All I need to really care about is the region R, right? So if they didn't give me this, then I'd have to start investigating the surface and seeing what the projection is in the XY plane. They often just give you R, though, straight up. They're like, here's what R is, and then draw that, right? And that is indeed what we need to do. So let's go ahead and draw that domain of integration here. I know x equals 0 is a boundary of the region, and I know y equals 0 is a boundary. So these aren't just axes, these are boundaries, right? They were specifically mentioned. Then y equals 4 minus x is a straight line, and with slope -1, with a y-intercept of 4. 1, 2, 3, 4. Right? And then when x is also 4, y is 0. Right? So we have that. This is the region of integration right there. Top view. Okay. Awesome. So now let's make some decisions here. All right. We've been doing a lot of dx, dy, so let's do some dy, dx. And I think it's not going to really matter because up, down arrows here start at this horizontal line, which means a 0 gets put in, which is nice. So let's go ahead and do this. My integral is going to be the integral of x e to the y. And let's integrate with respect to y first. Okay. So if I integrate with respect to y first, these are up arrows. And it starts from y equals this horizontal line, which is y equals 0. And it goes up to y equals whatever this line is. Oh, this line was given. And y equals 4 minus x. Nice. Don't have to think too hard there. Then these arrows start at an x value of 0. And they go through to an x value of 4. So 0 to 4. And there's your setup right there. So sometimes you'll be asked just to set up a double integral. That's what I mean. You would give it in either terms of dy dx or dx dy. It'll probably request what order it is, but if it doesn't, you would have to just set it up in some way. Okay, let's go ahead and get to this. So this is going to be the integral of from 0 to 4. Now, integrating with respect to y, this is going to be a constant times e to the y, right? And so that is going to be the integral of e to the y with respect to y is e to the y. So that is the antiderivative. And I am evaluating that from 0 to 4 minus x. Okay? Dx. Okay? So now I have to go ahead and plug this in. So I'm going to get integral from 0 to 4 of x e raised to the 4 minus x minus x times e to the 0 dx. Okay. All right, and so now it looks like I need to integrate this. Okay. Unfortunately, this is not going to be great, right? Because this is not a u sub. If I let u be 4 minus x, right, du is negative dx. And there's no x that comes out to help me with the x in front, right? This might be an integration by parts integral. So this is the first problem that we've had. Are regular difficulties with anti-differentiation, right? So notice with these double integral problems, there's actually two main sources of difficulty. You could have a ridiculously hard setup of limits, and the geometry of the domain space is awfully hard. That's a possible source of difficulty. On the other hand, we have the regular difficulty we had in Calc 1 where the thing you're trying to integrate is just tough. So double integrals have this lovely feature of maybe being tough in both ways. Now, the setup of this was way easy, really easy. So here we're just getting the natural problem of, oh, there's an integration by parts, x times e to the linear factor. So that could be integration by parts. Now you have a couple options here. You could go look up the integration by parts formula, which is totally reasonable and totally fine to do. Or you might consider switching the order. Maybe we should have done a dx dy, but I don't know if that would help. I'm not sure that helps, right? Because just thinking ahead here, I'm going to have to integrate this, and this is going to be x squared over 2 times this. And then I'm going to have to plug in a funky y. So it looks like if I set up the other way, dx dy, it looks like this might be x squared e to that, which is worse, which is worse. That would be 2 integration by parts to do. So it looks like we just have to bite the bullet and do an integration by parts here. So let's go ahead and remind ourselves about integration by parts. All right. So for integration by parts here, we're going to need, let's in fact just do it over here, the integral of x e to the 4 minus x. That's what we're interested in. There. We have to pick a u, and we have to pick a dv, right? And the u I want to differentiate, and the dv I want to integrate, okay? So let's put the x here, and let's put the e to the 4 minus x dx here. Reason being, when I go to differentiate this, I'm going to get du equals dx. That simplifies. Instead of a power of 1, we have a power of 0. Great. We reduced power. That's probably a good thing. Now, the only difficulty I have now is I do need to integrate e to the 4 minus x. But that's actually not bad. Let's go over here to the side. The integral of e to the 4 minus x dx in and of itself is a u sub. Let u equal 4 minus x. Then du is negative dx. So a negative will come out. And now I'm integrating e to the u, which is e to the 4 minus x. And that's it, right? So the integral of that's not too bad. I'm just going to get negative e to the 4 minus x. Okay, now that we have our parts, we just have to remember that darn formula, right? Which is uv, so minus x times e to the 4 minus x. So uv minus integral v du this way. So v has a negative, so that negative out in front comes positive, and I'm integrating e to the 4 minus x dx. Oh, that's not bad at all. We just did that integral. That showed up again. So that means I'm finished. This is going to be negative x e to the 4 minus x minus e to the 4 minus x. Okay. So I at least got the antiderivative that I was seeking. The antiderivative of x e to the 4 minus x is negative x e to the 4 minus x minus e to the 4 minus x. Okay, thanks to integration by parts. Let's continue on. So now, my antiderivative of this is going to be this mess, negative x e to the 4 minus x minus e to the 4 minus x minus the integral of x, which is x squared over 2. Evaluated from 0 to 4. I don't know if I can squeeze it in on this corner, but I'm going to try, and I'm sorry if that's frustrating. So here we go, minus 4 e to the 4 minus 4, which is e to the 0. E to the 0 is 1. Nice. Check that one off. Minus e to the 0, right? Because 4 goes in, e to the 0 again, so minus 1. Minus 4 squared, 16. 16 divided by 2, 8. Okay. Then it's going to be a minus, so plus, plug in 0. That's going to be 0 times e to the 4, which is 0, plus, right, because minus a minus, e to the 4, plus 0. So I get a final answer of e to the 4, minus 4, minus 1, minus 8. That's going to be what? Minus 12, minus 13. So it's an answer, all right. There we go. E to the 4 minus 13. Okay. That is double integration, right? And so you want to practice setting these things up. You want to practice switching orders if necessary. I'm noticing some of these in the book will set up a certain way or ask a certain way. And then they will tell you, oh, you might have to switch the order on that, right? So look for that tough integrals, maybe switching it to the other order, right? Of doing that. I want to make sure I've covered everything else here. I'm not covering average value of a function, so you can safely skip that. So that's that. And I want to make sure, yeah, I basically covered everything here. Cool. Okay. So I think that's a great place to end for the week, right? With that. Next time, we're going to be talking about double integrals again, but this time we're getting another option to unpack dA. dA can be unpacked as dy dx or dx dy, or we can unpack it as polar. And you should be thankful because I skipped really nasty problems. Well, let me show you. Let me show you. I know I said I was ending up the video. I'm sorry. I'm sorry. But I have to show you this real quick. Yeah, the first example that they used here was this. Okay. Finding the volume of this. Right. And there's a point here that I want to make right here. Right, and so they say, okay, I want to find the volume of the solid z equals 4 minus x squared minus 2y squared and the xy plane, as shown in this picture, figures 14, 17. Yeah, right there. Okay, so that looks simple enough. I mean, okay, we have the surface, no problem, 4 minus x squared minus 2y squared. But look, it projects down. This is a circle. This is a circle, or an ellipse even. It might even be an ellipse. It looks like an ellipse. And so that's unfortunately the R that we have to deal with, that it's an ellipse in the XY plane. Yikes. But we're in rectangular coordinates, right? So yeah, the Y values are going from, bottom curve to top curve. So that's going to be, they have to come up with the equation of this ellipse, which in and of itself is not fun, right? And then they have to go from bottom curve to top curve, which involves these really nasty square roots, and then integrating the x from -2 to 2. And you can see that it gets a little ugly here, right? They start out, they integrate with respect to y, but now they have to plug in these ridiculous square root things. Now, luckily, it does simplify to this, and it actually looks pretty simple. Except it's not. This requires a trig substitution to integrate. And so they just pull this trig sub out of nowhere. And that gets it into that. And then, even so, that trig integral that they get is cosine to the 4, which is absolutely awful. Cosine to an even power to integrate over those is not friendly. And in fact, this book thinks it's so unfriendly. They covered something earlier called Wallace's formula that basically memorized some answers, a way to calculate this answer without having to do that integral, right? See what I mean? What a weird, hey, I just introduced a square, right? This problem, this is our first problem that we did. Now the second problem. Oh my goodness. So yeah, I don't agree with that being the second problem of double integration that you ever see. This should be like towards the last, like the thing I'm doing right now. Bottom line. Here's all of this to say. There's no reason to do this using rectangular coordinates. It's actually going to be a little bit cleaner and a little bit nicer, I swear, to do it in polar coordinates. I know polar coordinates sounds like it's more hassle, but it sure is going to beat having to integrate using these weird square roots and then getting trig subs all over the place and then having to finish it off like that. So, bottom line, we're going to invite polar coordinates in when they are useful. And they happen to be useful when your base is a circle or an ellipse or something else that is quite easily described in polar coordinates. Yeah, that's what we're doing next time, 14.3. And then we're going to talk next time as well about some applications of double integrals. What are they used for? And then somewhere around the horizon, triple integrals. Ooh, so fun. Yeah, the fun never ends here. So, all right, until next time, everyone, hope you have a great weekend, and I'll catch up with you on Tuesday. Until then, be well, and see you next time. Bye.